A little quiz, yeah. And you're going to have homework for the long weekend as well. That's going to be videos. Now, just videos. Just videos and a little quiz. All right, so we were talking about light before, and of course we did a lab in here, and we'll talk a little bit about that today as well. For example, we were looking at light as a wave last time, right? And this part of the wave, this property of the wave, the distance between crests, is called wavelength, and its symbol is which Greek letter? It kind of looks like an upside down Y. It's called lambda. Now, you guys aren't rushing for sororities or fraternities right now, but you should learn some Greek letters anyway this time. This is new. This is, sorry, I better draw it neatly if you're going to learn them correctly. This is lambda. Lambda kind of looks like a guy walking like this. Like leaning back and walking like that. So that is lambda. That's the wavelength. So you could think of this guy, this dude, like just kind of traveling like this. That's wavelength. Nu is frequency. It's like a V in the wind. So this is lambda. You don't really need to know nu or lambda, except for the fact that I will call them nu and lambda, and so I suppose you should. I mean, I'm not going to test you on, which one is called nu, which one is called lambda. So anyway, that's wavelength, and we have this equation that we started looking at, C equals lambda nu. So for light, C equals lambda nu, where C is the speed of light in a vacuum. Speed of light in a vacuum, which is equal to 3.00 times 10 to the 8th meters per second. Now, just a reminder, this is the same thing as writing this, okay? Per second is the same thing as writing seconds to the -1, and I remind you of that because you'll see that around. You'll see me write it like that. You might even see it in your book. So meters per second. In other textbooks, you might see 2.998 because this is not an exact number. This is a measured value. So here we're showing it with 3 sig figs, 3.00. So 300 million meters per second, 186,000 miles per second. That's how fast the light is going. Now you can use this, and we talked about this last time, but you're going to use this for your lab, because in the lab, and I'll go over this now in case you want to get started on your graph and stuff over the weekend, and which you probably do. The main thing about the lab is we want to put voltage on this side because that is our energy. Okay? Voltage, remember, is going to be what we're calling our proxy for energy. It's taking the place of energy conceptually. It's got the same units as energy. It's proportional to energy, so that is going to be our energy. And then on this side, this is where it gets tricky. I don't want you to put wavelength on this axis. I want you to put frequency. Here's the problem. You measured wavelength. So for example, let's say you got 409.5 nanometers. That was your wavelength. That's what you measured with the little blue thing, the Vernier LabQuest, and the fiber optic cable and the SpectroVis. So if that's what you got, then what you need to do, you need to do 2 steps. You want to try to get this to frequency. To do this conversion, you're going to use this equation, C equals lambda nu, and I've got more problems on this worksheet today to practice with this, but this is what you need to use. The problem is the speed of light is in meters per second. So your first step is actually to convert your nanometers wavelength into meters. And to do that, it's 409.5. And I think I went over this in last class, but it doesn't hurt to do it again. 10 to the 9th nanometers per meter. So this will come out to 4.095 times 10 to the negative 7 meters. And in fact, we are working in the range of hundreds of nanometers. All of our wavelengths are, from say 400 to 700. So you're always going to get a number times 10 to the negative 7. And if you don't, something's wrong. Now, the nice thing about this is, well, actually, let me go to the next step first. 2 is to solve for frequency. So solve C equals lambda nu for nu. So nu is equal to C over lambda. Because all I'm doing here is I'm just dividing both sides of this by C, right? No, by lambda, sorry. I'm dividing both sides by lambda, by the walking guy. Yes. Yeah, but I think wasn't like the blue or UV something around that, like 410, 411, 409? I don't remember. It just was in my head for some reason. That's in like the blue UV range, 400. Red is going to be like 6 to 700. Actually, I think the orange is in the low sixes, if I remember correctly. So that's roughly how it works. That's the visible. Visible light doesn't have a wide range. It's all in the same order of magnitude in terms of wavelength and frequency. It's a very small sliver of the electromagnetic spectrum. So I'm dividing both sides by lambda. Lambda cancels. And C equals lambda nu. So then this is going to be 3.00 times 10 to the 8th meters per second over 4.095 times 10 to the negative 7 meters. Now, I'll just do another reminder here because the other section was having trouble on this worksheet because of calculator input issues. So there's two ways to do this. My preferred way is to use the exponent button here, the double E. If you've got an 83 or like a TI-30 or similar products from other manufacturers, you have this E button. Now that E includes times 10 to the, E says times 10 to the, and then you put in whatever it is. So in this case, it's going to be 8. That's pretty simple. And then I can just say divided by 4.095 E negative, making sure I'm using the negative symbol rather than the minus sign, and then 7. So 7.33 times 10 to the 14th with correct sig fig. 7.33 times 10 to the 14th. Now this is a big hint for you because I just said we're working with visible light. It's all in the same order of magnitude. This is the order of magnitude you're looking for in your answers, 10 to the 14th power. If you don't see that, something's wrong. Okay? That's the frequency of the light. Now here's what you can do on your graph, because what are you going to do with these numbers down here? You're going to put those in exponential notation. You can put them in scientific notation, but it's going to make a mess. So here's what I would suggest. When you label this axis, here's something they do all the time in science. You write nu, or frequency, and then you write times 10 to the 14th power. And then when you put in your spreadsheet, instead of putting in the scientific notation number, you just put in the coefficient, 4.095. You follow? And then it says, right here, this says times 10 to the 14th. So people look at this graph and they know, all right, whatever number I see here, I'm going to multiply by 10 to the 14th. So this might say 0, 1, 2, 3, 4, 5, 6. And this point here, 4.095, would plot out somewhere like this. And then I know that's 4 times 10 to the 14th. This just means whatever number you see on the x-axis multiplied by 10 to the 14th. It's telling that to the reader or the viewer of the graph. So, and again, what's just a reminder on the whole point of this lab. What are we going to see here? Are we going to see this? 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 Are we going to what are we going to see for the relationship between voltage and frequency? That's our question. What would you call what? Which part? That squiggle? That's the relationship. And it's complicated. Yeah, Kayla. Okay, good question. I'm glad you brought that up because I was going to forget. I was going to forget to talk about that. So uncertainties in voltage. So you're going to have both vertical and horizontal uncertainties, and you want to make sure you include them both. For voltage, this is just going to be the average deviation of your voltage because you got 3 measurements for voltage, right? Now on this one, this is going to be, so on this axis, it's going to be smaller. All right, so this one's going to be smaller, I think. It depends. Some of you got pretty precise voltages too, but this is going to be from the peak. So if this is like my graph, I was looking at that graph on the device, on the Vernier LabQuest, and I did something like this. We're getting something like that from my uncertainty. Right, that was for the wavelength. Okay, so what do we do? How do we translate the wavelength into frequency with the uncertainty? Right. Okay. What I think I think the easiest thing you could do, one way would be to actually convert each of those, like if you have a midpoint and then the two ends, convert each of them to frequency separately. But the other way, I think, is to, if you get something like this, let's say you have, so uncertainty in wavelength, or frequency, I should say, because we're wanting to plot frequency, which is what makes this a little bit complicated, because we're converting it to frequency. So let's say I have 409.5, actually it's not going to be like that. Let's say it's 409 plus or minus 5 nanometers. So that's something like you might see. Plus or minus 4, plus or minus 5, 6 nanometers. Convert this to frequency. Convert this to frequency. No, you can't say plus or minus 5 because their units are different. This would be 7.33 times 10 to the 14th per second plus or minus 5 nanometers. They have to be in the same units. Right. Yeah, I'm pretty sure somebody in some troll on YouTube is probably going to correct me on that, but yeah. All right. So, but I think that's what you can do. So that just means you're going to have 2 conversions to do on each of the. This is due Monday night at midnight. I'm just kidding. This is due. When did we finish this lab? When did we finish the data collection?
7:45 on
Thursday? No. We finish it Tuesday. Okay, so let's say Tuesday. What would be the the 4th class day? We meet today. So it's today's 1. Then we meet when? We meet tomorrow. That's 2. Today's Thursday. Okay, we meet today, tomorrow, and next Thursday, and next Friday. So it should be next Friday at midnight.
Can it be Saturday at midnight? Oh, we don't. Yeah, but we didn't know how to do the math until today.
Um, Let me see just a second. Hang on. If I.
You're not a junior.
Mm, no, I was trying to figure out what the next class would come out though, but they're gonna. Those guys are doing theirs today, and they're gonna come out on Friday, next Friday too. So, plan on next Friday at midnight, unless I have, um, unless I have some kind of, unless I develop a heart over the weekend. Plan on completing it by Friday. Yeah. All right. So, any question on that? Just the new. You're gonna get practice on this worksheet too for that. Any questions on it? Okay. So we were talking about light, and we've been talking about light as a wave. We've been talking about light as a wave. Now we want to move on and talk about light as a particle. And actually, this is going to kind of cross over with our lab report. We want to talk about light and energy relationships. You've already gotten a hint about light and energy relationships because when I did that thing with the incandescent bulb and I had the rheostat, and as I turned, did we do that one? I turned it up and you saw that the blue and UV started to show up as it got hotter, as I put more energy into it. So you've already seen some of this, and you've already seen from the lab that the blue and UV bulbs took the most voltage to light up. Right? So we already see something about this. Now in your hypothesis though, we got to get more specific. So rather than just saying higher frequencies require higher energy, which they do, you're going to want to say, is this going to be linear? Is it going to be exponential? Whatever. So these are kind of our objectives. And we are moving on now from light as a wave. As we've discussed that a little bit, we're actually going to return to that, to the kind of wave concepts later on in the week, maybe tomorrow. There was a guy named Max Planck, and I think Max Planck, and he was looking at something called black body radiation, and this is early 1900s. It might have been like 1900. Is that actually the date? I'm not sure. I should have checked this. Anyway, he was looking at black body radiation. Now, a black body is, in physical terms, in physics, is think about, like, if you have an electric stove, think about the coils on the top of the electric stove. Right? It looks black when it's cold, and then as you heat it up, it starts to emit light. So solids emit light when they get hot. They emit light when heated. First, red, then orange, then they'll start to glow yellow, and then they would start to look white, and if you could get them really hot, they would start to look blue. And you saw this with the incandescent bulb. And it turns out, and I've got a little video up there, if you want more detail on what he was doing, take a look at the little video about Max Planck. It's only like 5 minutes long. It's not required, but he was working for a manufacturer of light bulbs, and they wanted to know what's the optimum temperature that we should have the filament heat up to get the most light out of it. Here's the problem. So he was working with incandescent light bulbs. Physics, current physical theories, so current, in his time, physical theory made the wrong predictions about this. And so he was trying to solve this problem. Classical, what we call classical physics, that was classical physics is physics before quantum mechanics. So current physical theory, I should say classical physics. They predicted the wrong result. Specifically, when they predicted this. If this is a graph of frequency versus intensity. So intensity is like the brightness of the light. Think about that light bulb I had as I turned it up. Different colors got brighter. That's brightness is on the y-axis here. The color is on the x. This is what we actually see. You see kind of a normal distribution. And this would be your red, orange, yellow, green, blue, violet. And that's so if yellow is the maximum here, that's why the light kind of looks yellow coming out of that incandescent bulb. The surprising thing is classical physics predicted this for the incandescent light bulb. In fact, classical physics predicted this for everything, every solid object. And this was a major problem because it was wrong. And like if you're trying to use physics to solve the light bulb problem and say how can we make more light out of a light bulb, it's not going to help you because light bulbs aren't blue when you turn them on. So the whole thing was wrong. So what Max Planck did was Planck made an assumption. And if you watch closely as I write this stuff down, you might see a hint about your lab. Planck made an assumption that the vibrating atoms in the filament, or in the black body, because when something heats up, it's because the atoms are moving faster. Did you know that? When something's hot, the atoms are really moving fast. When it's cold, they're moving more slowly. Now, remember when I did the thing with I said if I have a charged object and I'm moving it, it makes waves in the electromagnetic field? So here's what's happening. In classical physics and in the mind of these guys like Planck, those atoms are vibrating and they're making waves in the electromagnetic field, which are light. So the atoms are the oscillators, they're vibrating, and the light is coming out from that. So here's what he said. He said those atoms could only gain or lose energy in certain increments. Increments. And we could also call this packets. So there are little packets of energy where the relationship looks like this, where nu is the frequency of the oscillator, the frequency of the vibrating atom, in other words, how fast is it vibrating? H is a constant called Planck's constant. I don't know if Planck called it that, but people now do. Planck's constant, which is 6.626 times 10 to the negative 34 joules times seconds. And then E is the energy in joules. So we measure energy in joules, that's the SI unit. And basically what happens with constants, and you're going to see this in the future too, what happens with constants is they have funny units a lot of times. Joules times seconds, what's up with that? What does that even mean? It's basically to cancel out the other units. So This seconds right here is going to cancel out the per second from the frequency, and you're going to end up with just joules as your energy. So that's why it has these weird units. It's not like it has some deep significance or something like that. Now, this probably doesn't mean a whole lot to you, but here's what I want you to get out of this. So when he said this, those vibrating atoms can only lose energy in certain packets. So let me show you kind of an example. Let's say you know what? Hang on. I got to untether myself here. Alright, so let's say these styrofoam peanuts are energy. These are energy. The basic idea is what he's saying is that energy is quantized. And this is where the idea of quantum mechanics came from, was Max Planck at first. Energy is not like a fluid where you can lose or gain any amount that you want to, like just pour out whatever you want. It's grainy like sand. And so if you're going to gain or lose energy, you're going to do it in increments. Let's say this was all my energy. I can't do this. I can't do that. I have to keep the packets whole. And so that means not only can I gain or lose only certain increments of energy, I can only have certain increments of energy. So you can't say like, oh, that atom could have any possible energy in it. You couldn't say it could have an infinite number of amounts of energy. That's not true. It's like increments. Think about a volume control where it's just smooth and you keep turning it and the volume keeps going up. And then think about a volume control where it clicks and it has maybe 10 levels. What Planck was saying is the atoms are like the volume control that clicks. And it goes from level to level, and you can't put it in between levels. And when he did that, he solved the problem. So this solved the problem, and he was able to improve the light bulb as a result. This solved the problem. So it's kind of weird, and I know, you guys haven't had physics yet, so it probably doesn't, maybe it doesn't even strike you as weird. But what we're going to see later on is that this is actually true for everything. So like even like a baseball, for example. A baseball can actually only have certain energies. And a baseball can actually, therefore, can only move at certain speeds. It is not possible to move a baseball at any conceivable speed. It can only have certain speeds. Now the thing is, as particles get larger, so as you start with the size of an atom, this effect is very noticeable. As they get larger, then the increments become smaller. That's why we don't notice it with a baseball, because even though a baseball gains or loses energy in certain increments, we don't sense it like, you have to throw it at this speed or this speed or this speed. Because the increments are so close together, it seems continuous. It seems like you can throw it at any possible speed. But my point is that this idea of the quantization of energy, the fact that it's in increments, is universal. It's true for everything. Just not noticeable at the scale of a human being. So this solved the problem. Enter Einstein. And I'm going to throw this out there. I think the date was 1903. He was looking at something called the photoelectric effect. And for this, I've been talking long enough, so let me show you a little demo of this here. So we just shined two LEDs at the glow-in-the-dark vinyl, And we saw that the red didn't make it glow, but the blue did, right? Now it's also interesting if you look at these little LEDs. This one, the UV, takes two 3-volt lithium coin cells. So those little round like watch batteries, this takes two. The red one takes one. Is that surprising? Think. Okay, so the red one appears brighter, right? But this is an important point. The red one does appear brighter, but we've got to keep in mind that the UV one, we can't see the UV that it's giving off. So that could be part of it. But remember too that brightness isn't the only factor. When you did your lab, they were all at their dimmest when you measured the voltage. And what did you find? You found that the blue and UV took more voltage than the red. And that's what we're saying here. This one only takes one battery, this takes two. It actually requires more energy to make the UV light than it does to make the red. And so let's put this in a form of a graph. Oh, sorry. Sorry. So let's make this in the form of a graph. And we'll do a few different graphs. The first graph, we're going to put the response right here. And over here, we're going to put the frequency. Here's what we would find if and we used to do this as part of the lab, but it took too long. We would hand out little pieces of vinyl, glow-in-the-dark vinyl. We'd shine all the different LEDs on it. Here's what we would find. In terms of the glow, we would get, if this was red down here, orange, yellow, green, we would get no response until we got to blue, and then violet and UV, we would have a response. So this is a threshold effect. We would get no response until we got to blue. So there would be a certain minimum frequency required to get the response. And I just messed myself up by allowing AVG to update here, but so how can I, oh well. Now what Einstein was doing though is he wasn't actually working with glow-in-the-dark stuff. As fun as that would have been, that's not, he was working with something much more kind of boring. And that was, there are these metals, and this is what's in a light sensing device. Again, this is the photoelectric effect. I'm drawing it up here because I can't scroll down right now. And it turns out that when you shine light at these certain metals, like lithium or something like that, you have light, then certain frequencies of light will make electrons get kicked off of the metal. You can actually knock electrons off of the metal. And that's how those light sensing devices work. And this is the same thing with like lights that turn on when it gets dark out, right? They turn on when it gets dark because they have a little sensor at the top. And right, and car lights can do the same thing, like daytime running lamps and that sort of thing. Oh, come on, this is really going to make it difficult for me to... All right, so we can make a response in the circuit, and that's how the thing works, because the circuit can detect if electrons are getting kicked off of the metal or not, and it can make sure you're not going to crush your dog under the car door or something like that. Now, this would, if we put this on this graph, the response in this case would be the number of electrons ejected from the metal. Now, I'm making a shift here now. I'm not talking about the vinyl anymore. I'm shifting over and talking about this metal. our y-axis now is the number of electrons kicked off of the metal. In other words, you don't get any kicked off until you get to a certain energy. Now, this could not be explained by classical physics. Sound familiar? It could not be explained by physicists at this time in history. And so Einstein was looking at this and trying to explain it. And he realized it could be explained if light were a particle. With energy equal to h nu. And so this is actually called the Planck-Einstein equation because it's the same one. Same equation Planck used. He's interpreting it a little bit differently. Now, instead of the frequency being the vibrating atom's frequency, the frequency is the frequency of light. H is still Planck's constant, still the same. He didn't change the equation. He just changed its interpretation. This is still Planck's constant, and this is the energy of the light particle of the singular light particle. This equation gives you the energy of a single photon because that's what we call a light particle. Photon. It's not just for Star Trek. This is what we call a particle of light. And then, so let's look back up at when I started this today. I said we've got some objectives. One is to look at light as a particle. So that's what we're talking about now. Light as a particle started with Einstein. No, it didn't. Because even Isaac Newton thought light was a particle. So it's a very old idea, but Einstein revived it because up until between Newton and Einstein, it was really popular to look at light as a wave. Did I tell you about Einstein's hat pin experiment? Newton's? Yeah. So, no, Newton. That was Newton. No, Einstein wasn't that hardcore. I mean, he was good, but he wasn't as hardcore dedicated. So anyway, I hope he didn't hear me say that. So this is the energy of a light particle. Now, what am I saying here by saying that we can't explain it? If light is a wave, then why would it act like this? Why would you get no response, no response, no response, no response, bam, something happens? Here's how you can explain it with a particle. Have you ever played, all those games at the fair are scams, of course. I hope that you know that. But there's a game, so when they're trying to call you over to play your games, they are trying to rip you off. All right? Just a tip. Just in case you don't know. They're all tricks. They all have tricks. So there's one that looks really easy. Oh yeah. No. Yeah, right. Okay, so listen. This one is, I don't know if you've seen this one. I haven't seen it in a while, but there's bottles on a shelf and you have a baseball and you have to knock them off the shelf. Now, it looks easy, but as all those games do, they're not, probably because there's like a magnet in the bottom of the bottle or something like that. But here's the thing. You have to hit the bottle with a certain amount of force or it's not going to fall off the shelf. You follow me? So if I want to knock this bottle off, I have to hit it with a certain amount of force. Is this how you look when you throw something? I don't know. So this guy he has to hit that bottle with a certain amount of force or it's not going to fall off. Now, so here, this would be like the speed, in this case, this would be the speed at which he throws the ball on that axis. And you'd say the bottles aren't going to go anywhere until he hits them with a certain speed, a certain energy. So that's the idea of a particle. what Einstein is saying is that literally the reason it doesn't work is because the photons are not hitting it hard enough until they get blue. At that point and above, they have enough energy to knock the electron loose. Now, if you can make some more graphs too. You can say, let's say we increase the frequency again, and here's our blue. But instead of measuring the number of electrons, let's measure the kinetic energy of the electron that is ejected. Ke is kinetic energy. Here's what we would see. Now let me explain this graph to you. If you're throwing that baseball at the bottles, you have to throw at a certain minimum speed to knock the bottle off, right? You also have to be on the good side of the person running the game, because whatever kind of scam they're running, you want them to shut it off for you so that you can win the cheap prize that's worth much less than the money you paid to play the game, right? But let's say you throw it harder than you need to knock it off. What happens? The bottle goes faster when it comes off. So that's what you find with the photoelectric effect. If you actually put a little detector and you measure how fast the electrons are going when they get knocked off, let's say I shine UV light on it. I'm not going to change the number of electrons that come off, but they'll be going faster. I'm switching back and forth between bottle and electron here. They'll be going faster. If I hit the bottle just enough to knock it off, it's just going to do that. But if I hit it with more energy, it's going to go flying. Right? So if I hit it with enough energy, it might explode, and the guy will be like, he'll have like glass in his face and everything. But that's probably not likely. Okay? All right. Now, there's another graph that we can make. And this is the last graph. I don't know if you like graphs as much as I do, but I hope so, because this is intensity of blue light. So listen, we're doing a new experiment now. And instead of increasing the frequency like we were doing in the first two experiments, this is supposed to say new, this is frequency. Instead of increasing the frequency like we've been in these other two graphs, increasing the speed or the energy of the particle, we're going to increase the number of particles. So intensity is brightness. Now this, if you think about this, because this comes into play in your lab. We were able to change the brightness of the LEDs, right? You increase the voltage up to a minimum point, and it turns on, right? You keep going, what happens? It gets brighter. So this is what we're showing here. Now that's intensity, and now we're going to put the number of electrons ejected again. And here's what we see. We start with no blue light that we're shining on it. And as we shine more blue light on it, we get more electrons ejected. That's because intensity is the number of photons. So a number of photons shining on it. In other words, so this, let's go to the fair game activity. You're at the fair. Let's say you're just so into this, you say, I want to buy 500 baseballs. I want to play this game 500 times. All right? So you're going to throw 500 times. Now you're going to knock more bottles off the shelf. Okay? So when you shine a brighter light on it, it doesn't change whether or not an electron gets knocked off. It just knocks off more electrons. And all three of these graphs are what Einstein looked at. He looked at all three of these experiments. They were all classic experiments which were inexplicable with classical physics. But when you looked at light as a particle, you could explain them. In the same way that we can explain the bottles getting knocked off the shelf, which really doesn't happen because you actually get ripped off. Do you know there? You know what I'm talking about with a scam. Do you ever play that game where there's a red circle and you get 5 metal discs and you're supposed to cover all the color with the disc? Have you ever played this one? And the guy's sitting there and you walk up and he does it every time like that fast. Like he just goes tuk, 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 and he drops it and it's done. And so then he's like, "You want to try $5?" So you take the $5 and you can't do it. Why? I don't know how it works, but I'm telling you, you're getting ripped off. He's got the same vibe, but he's got some kind of a magnet or something in there. I guarantee. He's got like a little pedal that he's pushing under the counter, and it's making you not win.
Sketchiest people running those things though.
It is a scam.
Ex-con, pedophiles.
That's it for